Welcome to the semester math review for Analysis and Approaches HL1. We're going to be covering chapters 4, 11, 7, 8, 9, 14. Yeah, I'll put the timestamps somewhere here. We're going to start off with Core 2, which is sets. A set is a group of things, and the things inside a set we call elements. For example, if you had a set, the alphabet, the elements would be all of the letters that are in the alphabet. We have some notation for sets. For example, if you want to say something is in a set, you would say it is an element using this funny E-looking thing. A is an element of uppercase A, which is the set. Element set. If you want to say something isn't in a set, you would do the same thing, but you cross it out. A is not an element of A. If you want to talk about the relationship between sets, you can use subsets. For example, if all of the elements of B are elements of A, then B is a subset of A. There are no elements that B has that A does not have. However, this definition of subset, these two could be equal. So if you want to say a subset that is not equal, for example, you would say B is a proper subset of A. And it's the same C-looking thing, but without the little plate that it's sitting on. And of course, if you want to say the sets have all of the same elements, you would just say they are equivalent. Now, what if you want to talk about elements from multiple sets, or talk about elements that are only in both sets? For the former, we would use a union. When we say A union B, this means that we are talking about all of the elements in both sets. If we want to talk about the elements that they both share, and only the ones that they share, we would use an intersection. The intersection between sets A and B are the elements that they both have, not just one has. One other special thing is a prime set. Set A prime is the set including all elements that are not in the set A. Basically everything outside of set A. If we want to talk about the number of elements in a set, we would talk about n of A. If you say this, n of A is 12, we know A has 12 elements. However, if you said something like using bracket notation and said A equals 12, this would mean that the number 12 is itself an element of A. There are some special sets, and we have special notation to describe them. First is the null set. It's like an O with a cross through it, a slash. This is a set with nothing in it. It's empty. It has no elements. The set that has an n is a natural set, and it is the set of all natural numbers. Natural numbers are all of the counting numbers or positive integers. If you want to talk about integers, we'd use z. Set of z is all integers, and you can specify positive or negative with a plus or a minus. The set of rational numbers, or numbers that can be expressed by a fraction, is q. Finally, the set of all real numbers, or numbers that do not have the number I, which is the square root of -1, that set is r. It looks something like that. I don't know exactly how to draw them. Yeah, we can express sets visually using Venn diagrams. So how would we draw this? First, we're going to talk about the universal set, or U. This is all of the elements that we are concerned with. It basically sets the parameters of our world that we're dealing with. For example, if U is going to be all real numbers, we wouldn't consider any numbers that are imaginary. And U is represented with a box. If you're drawing a Venn diagram, you want to make the box pretty big because nothing is worse than being stuck in like a really small box. This box is U. Inside the box are all of our sets, and they are circles. Here we have two sets. We have set A and we have set B. If we wanted to put the elements that are inside just directly, set A has elements 1, 2, 3, and 4, and set B has elements 4, 5, 6, and 7. In their intersection, they both share 4, and that's why 4 is there. If you didn't want to put each element, for example, if we're talking about how many oranges are in baskets, we wouldn't want to just put like orange number 1, orange number 2, like that would take super long. We might just want to talk about how many elements we have. And when we do that, we're going to use parentheses. For example, the number of elements that are only in set A and not also in set B is 2. The number of elements that are in both sets is 1. And the number of elements that are only in set B is 5. It's good to note that 5 does not include the 1. In total, there are 6 elements in B, and in A, there are 3 elements. You don't subtract them, don't do that. And let's say out here it's a null set, there's nothing outside. So let's label this. This whole thing is the union of A and B. Right here is their intersection, and out here is the prime of their union. If I wanted to talk about, for example, the prime of A, everything outside A would be all of this. Everything outside of this circle of A. All of that is A prime. If A prime is equal to set B, and B prime is equal to set A, they are complementary sets, they're complements of each other. They have no intersection. There is also nothing outside of them. It would look something like this. No intersection, and they completely take up all of U. Pretty cool. Now finally, we're going to talk about notation. Specifically, notations with names, or ways that you could describe a set. We talked about general notation in the beginning, but this is more specific. The first one is going to be brace notation. These things are braces. They're also known as curly brackets, and when you're using brace notation, you put a list of all of the elements inside the braces and then set it equal to the set. This tells us that inside set A, there are the elements 1, 2, and 3. We also have my personal favorite, set builder notation. Set builder notation also uses braces, don't get confused about that. But basically, you're going to say that inside A, there is X. X means any element. And then you're going to use this line, which means such that, and then you define the limitations or the restrictions on X over here. X is an element of B. Or maybe X does not equal 0. And that's how you do that. Finally, we have interval notation. And here, you would say something like X is an element of A, and then you would define the range of X, such as it goes down to negative infinity, up to 3, and then it includes 3. Union includes 8, and then goes up to 10. It doesn't include 10. Something like that. Now we're going to talk about Core 11, Chapter 11, probability. Probability is pretty cool. One thing to note is that probability is not chance. Chance is a percentage. There is a 15% chance that it's going to rain. A probability of rain would be 0.15. The probability is always a number between 0 and 1. 0 being it's never going to happen, it's impossible, and 1 being it is certain it is going to happen. In the real world, there are no certain or impossible events. Everything is just approaching. It's very, very highly likely the sun is going to rise tomorrow. However, there is a incredibly small probability that it won't. Nothing's really certain. There are different ways to find probability and work with it. One is experimental probability. This is where you get probability from actual real-life data. If you want to find the probability of event A, it would be equal to the number of times that A happened, event A, and then I would divide that by the total number of events. This is also called relative frequency. Frequency being the number of times that an event occurs. Now we also have theoretical probability. This is based on things that we know are true, not based on actual events and data that has happened. So instead of the number of times that A did happen, we would say the number of times that A could happen. And then it is again under the total number of events. Like if I wanted to find the theoretical probability of getting heads on a coin flip, the number of outcomes that are outcome A, that's 1. That means I land on heads. Total number of outcomes possible, that's 2. And so the theoretical probability of her getting a head is 1/2. Whereas if I flipped a coin, say 20 times, and I got maybe 12 tails and 8 heads, it would be 8/20, and that is a different probability. And so theoretical and experimental can differ because of how we get them. When we're working with theoretical probability, we have certain equations that we use to find different information that we want. So for example, we want to find the probability, theoretically, of event A happening or event B happening or both. So what would this consist of? Well, the probability of event A happening is part of this probability. So it would be equal to the probability of A and also to the probability of B. We would add probability of B because we are counting whether A or B happens, like it's an or, we're including both. However, if A and B intersect, then we have counted the intersection in both of these probabilities. So we've counted it twice. Therefore, we need to subtract the probability of both A and B happening. You can think about it in a Venn diagram kind of way. Let's say I have like 2, 1, 3. When I count all of A, I count 3. And when I count B, I count 4. But I counted that 1 in the middle twice, and so I would need to subtract 1. And that is where we get our equation for the probability of a union. Now we also have the probability of an intersection, and this is equal to the probability of A happening times the probability of B happening. Now, this might not make intuitive sense. Why do we multiply them? Well, to answer that, we're going to have to think about what probability actually means. Let's say that event A has a probability of 1/4. Let's say that event B has a probability of 2/3. Probability of A means that out of all of the total possible outcomes, 1/4 of them would be A. For probability B, this means that out of all of the total outcomes, 2/3 of them would be B. If we want to know A and B happening, let's say that A happens. A has a 1/4 chance of happening, and then B, on top of that, of this becomes the new U. This is now all of our events that we're concerned about. Of this, there is a 2/3 chance of B. And so you're taking the 2/3 chance of the already 1/4 chance. And since it is 2/3 of 1/4, we multiply them together. Let's talk about diagrams that we can use to represent probabilities. A really nice one is the lattice diagram. You can only use it for 2D situations. This is the probability of me flipping 2 coins. On each axis it is 1 coin and it's 2 outcomes. You kind of make a grid, and then their intersections are all of the possible outcomes. and it tells you the probability. Getting a heads on this coin and a tails on this coin, it's 1 out of 4 because it is 1 literally out of 4. Now, a problem with this, you have to express every single possible outcome. Basically, if you have a lot of outcomes, you'd have to list them for a long time, so that can get tedious, but this is helpful sometimes. We also have tree diagrams. This is the first event. Let's say there's 2 possibilities, event A and event B, and then we got C and D and C and D. It basically shows you all of the pathways that you can take. Here is A happens and then D happens, and then you can count the number of outcomes after both events. There's 4. And the handy thing about this is that it doesn't rely on like counting to find the probabilities. You can write the probabilities on it. You can clearly see the probabilities, and then you can multiply along the path. The thing about these is that they're both theoretical, but we also have one for experimental data. That is the two-way table. Within these boxes, you would put the number of times that event happened. Like event A and C happened, let's say 10 times. This box down here, the total, that is the total number of times any event where event C happened occurred. So C happened 12. And then you can either add down this way or this way to get the total number of outcomes that ever happened. And it's good to check that both of them add up. It's really nice. Now we're going to talk about independence and dependence. Independence is when the outcomes of 2 events do not impact the probability of the other outcome occurring. For example, the probability of it raining and the probability of me choosing a red shirt to wear, those don't impact each other at all. One is actually 0, that's the only impossible event, me wearing a red shirt. And the other one is like 100% because I live in the place where it rains every freaking day. However, some outcomes do impact each other. For example, if I wanted to find the probability of my car breaking down, and then the probability of me driving to work. If my car broke down, I would not drive to work. That would impact the probability because that outcome occurred. And so we can talk about dependence. One rule for independent events is that their intersection is equal to their probabilities multiplied. If you want to find the intersection of dependent events, it would be equal to the probability of A times the probability of B given A. Here's that given sign again. We saw that earlier. And this means that event A happens given that A has already happened. So it's not the total probability of B out of U, it's a probability of B out of A. And from this equation, we can derive the equation for this bad boy. Probability of B given A equals the probability of their intersection divided by the probability of A. Okay, so I realized what I did wrong. When I was trying to explain this, I forgot the most fundamental part. So when you think about B given A, you have to remember that the probability of B changes when A has already happened. So if you don't want to just say, oh, like probability that I will drive to work, that would be like maybe 7 out of 10 or something. But then given that your car broke down, that's a new probability of B because A changed the outcome. So then it would be 0. And so that is what B given A means. And that depends on the situation. Okay, back to the actual video. We also have some handy formulas that we use called Bayes' theorem. Bayes' theorem states that the probability of event A happening given that event B has already happened is equal to the probability of B given that A already happened times the probability of A all over the probability of B. Core 7 is traditional trigonometry. This is going to be a very nice core, very nice unit. I like it a lot because it can be boiled down to basically 3 things: the functions, bearings, and then projections and 3D shapes. Projections and 3D shapes kind of combine. So let's talk about the functions. We have sine, and sine of angle theta is equal to opposite side over hypotenuse, saw. And then cosine of theta is equal to adjacent side over hypotenuse, ka. And then tangent of theta is equal to opposite over adjacent, toa. SOHCAHTOA. And this is all within a right triangle. It will not work with non-right triangles. It's not going to work for you. We also have the inverse of them, or the arc functions. Arc sine of opposite over hypotenuse equals theta. Boom. These are our functions. Now that we have that out of the way, we can apply it to things. You can apply it to triangles, and you can apply it to bearings. Bearings are a way that we communicate location within an area. It's always in regards to true north. Let's say this is a person, and then this is a person, and north is this way. The first thing you do is you label north from the points. And if I wanted to find the bearing of this person, let's call them A, from this person, let's call them B, you would calculate the angle between north and then going counterclockwise to the line they're collinear on. This is the angle. I'll call it theta. And that is really cool. Solving bearings, you'll probably have 3 points. So let's say we have like another dude down here. And so this is the bearing of point C from point A. This is the bearing of point B from point C. And as you can see, we made a triangle. And often it'll be a right triangle, but you probably won't know that until you do some stuff. Some key things to use: alternate interior angles, alternate exterior angles, corresponding angles. That is because all north lines are parallel. So this angle and then this angle are equal. You can find things using those. And then once you have a right angle, then you can apply tangent and cosine. If you have the distances, it's cool. But the things that you have to know, you go counterclockwise from north, and remember that point something from something means you start from the north of the thing after from. You're going to be starting from A, and so you do the angle thing on A. And that is a bearing. Finally, we're going to talk about projections. Projections are basically a shadow within a 3D plane. If you want to talk about the projection of this line, it goes through the plane, onto the plane, you can basically imagine a shadow is being cast down. And the shadow looks something like that. It is directly underneath. It is like you basically took all the points and you just dropped them down and formed the projection. That is the projection. And to find the angle between a line and a plane, you would find the angle between the line and the projection of the line on that plane. And that is the key thing. From there, you can apply all of the trigonometry terms to find things. And also don't forget Pythagorean theorem, or the ABC theorem, as it is properly called. That is how you can also find side lengths of the right triangle if you don't have them. And that is core 7. Nice. Hold on. We forgot about talking about shapes. You need to have a strong knowledge of geometry to do core 7 work. So we're going to talk about some traits of some 2D shapes. Let's start off with triangles. In an isosceles or an equilateral triangle, the altitude is going to be a perpendicular bisector of the base. In squares and rhombuses, the diagonals meet at 90-degree angles. And they also bisect each other. Kites, their diagonals also meet at a 90-degree angle. If you have a circle, point of tangency, a line directly drawn down to the point of tangency from the center, it will meet the line that has the point of tangency on it. It'll be a 90-degree angle. If you have a chord in a circle in a center, a line drawn from the center to the chord will bisect it at a 90-degree angle. And finally, an angle of depression is an angle that is from a horizontal down. An angle of elevation is from the horizontal and then up. All right, on to core 8. All right, core 8 is probably the biggest core until quadratics. It has a lot of stuff, and it is all centered around the unit circle. The unit circle has a center on the origin and a radius of 1. It is really cool because the coordinates of any point on its circumference, the angle counterclockwise from the x-axis, the positive x-axis, to that line from the center to the point. That's angle theta, and the x value of the point is equal to cosine of theta, and the point y is equal to sine of theta. The way that we measure the unit circle is with radians. Radians are super cool. How do we convert between degrees and radians? The number of degrees divided by 180 is equal to its equivalent number of y radians divided by pi. Radians are super useful because they give us a ton of awesome formulas that we can use. And specifically, we're going to talk about arc length and sectors. And the formula for arc length L is equal to the angle theta, right here is theta, times r. Now say you wanted to find the area of this sector. We would use the formula A equals theta times r squared over 2. Remember how the unit circle has a radius of 1? Well, that means that no x value will ever be greater than 1 because the biggest x value of a point is going to be right here. It's going to be when y equals 0, and it's going to be when x equals 1. Or it could be when x equals -1. -1, 1. So therefore, cosine of theta is going to be greater than or equal to -1. It's going to be less than or equal to 1. And the same thing is true for sine. The greatest y value is going to be up here at 1. And the smallest, or most negative, y value is going to be down here at -1. And so sine of theta has the same restrictions as cosine. Now, tangent, it's a little weird. So let's say that you have a line. It's tangent to the point 1, 0. If we were to extend this line that goes through the center and the point we're talking about, we would get a length, and this length is tangent of theta. We can also use sine over cosine is equal to tangent. Another thing you may have noticed, the cosine and sine form a right triangle. Right here is the cosine, because this is the point, the x-coordinate, and right here is the sine, that's the y-coordinate. And so, using the ABC theorem, or the Pythagorean theorem, we know that cosine of theta squared plus sine of theta squared equals 1. If we only have sine of theta, we can find cosine of theta. I talked about this next thing a bit in my memorizing unit circle video, which you should check out. Information about what happens in different sectors. The unit circle spans all 4 sectors as it is centered on the origin. Any point in sector 4, both sine and cosine are going to be positive because both points are going to be positive. In sector 2, the y value does not change, sine does not change. However, the x value changes, so it becomes negative. So any point in here, the sine is going to be positive and the cosine is going to be negative. Down in sector 3, they're both going to be negative. And in quadrant 4, x becomes positive again, and sine is negative. And this becomes important when we want to memorize the unit circle and when we think about the periodic nature of the unit circle. What do I mean by the periodic nature of the unit circle? Let's say we have one point here, and we rotate it around the origin either 2 pi radians or 360 degrees. It goes all around and it comes back. That angle, that's going to be theta plus 2 pi. And this point, that dot is back to where it started. That point is back to where it started. And so the coordinates of the angle theta plus 2 pi is going to be the same as the coordinates if the angle were just theta. And so from that, we know that their cosine and sine are going to be equivalent because they have the same coordinates. So cosine of theta plus 2 pi is equal to cosine of just theta. And the same is true with sine. Sine of theta plus 2 pi is equal to sine of just theta. These 2 points, those are called coterminal. There are other similarities too. If we reflected this point across the y-axis, the sine would stay the same. These are just the same point reflected over. This is also going to be equal to angle theta. And so this whole angle, this angle right here, that is going to be equal to pi, or 180 degrees, minus theta. And they have the same sign. So sine of pi minus theta is equal to sine of theta. Also, with cosine, we notice that if we reflect it across the x-axis down here, the cosine does not change. It has the same x point because we reflected it. Now, how do we calculate this massive angle right here? The angle that has the same cosine as this angle. Well, as we reflected it, this angle is also going to be theta. These 2 angles are the same. And so that angle is going to be equal to 360 degrees or 2 pi minus theta. And so cosine of 2 pi minus theta is the same as cosine of theta. This shows how periodic the unit circle is. We reach certain points where they have the same x, the same y, same sine, same cosine. That's very periodic. All right, let's talk about tangent. I'm going to discuss tangent only using our definition of sine of theta divided by cosine of theta is equal to tangent of theta. What happens to tangent in the first quadrant? Sine divided by cosine, they're both positive. Positive divided by positive is positive. So therefore, tangent in the first quadrant is going to be positive. Second quadrant, it's positive divided by negative. That's going to be negative. Tangent in the third quadrant, negative divided by negative. Oh, that's a positive again. Sector 4, that is a negative divided by a positive. That is going to be a negative. Before I dive into the really cool thing about tangent, I need to talk about one more relationship between cosine and sine. And this is not based on the unit circle. I'm going to just use a right triangle. Now, according to the triangle angle sum postulate theorem, I don't know. According to the rule that all angles within a triangle must add up to 180, this angle must be therefore 90 degrees minus theta. And so, if we wanted to take the cosine of theta, it would be adjacent over hypotenuse. If we wanted to take the sine of 90 minus theta, it would be opposite over hypotenuse. Oh boy, those are the same. And so, from this, we can derive the equation that cosine of theta equals sine 90 degrees minus theta, and like vice versa, sine of theta is equal to cosine of 90 degrees minus theta. Now we're going to discuss an interesting angle for tangent. Let's talk about tangent of pi over 2 minus theta. This is going to be equal to the sine of pi over 2 minus theta divided by the cosine of pi over 2 minus theta. We know that the cosine of pi over 2 minus theta is equal to the sine of theta, and that the sine of pi over 2 minus theta is equal to the cosine of theta. And cosine divided by sine, that's 1 over tangent. And so we know that tangent of pi over 2 minus theta is equal to 1 over tangent of theta. And now, let's talk about tangent of pi over 4 is equal to tangent of pi over 2 minus pi over 4. And that's because pi over 4 times 2 equals pi over 2. This looks a little bit familiar. We have pi over 2 minus an angle. And we know that tangent of pi over 2 minus an angle is equal to tangent of 1 over that angle. So tangent of pi over 4 is equal to 1 over tangent of pi over 4. Now we're going to go over one very quick thing with lines. We have a coordinate plane. We got some lines on this coordinate plane. We have a line that intersects the x-axis. x-axis. This is the line. It has 2 points. It has A and 0. That's this point because this is length A. And it has another point. This is length B and its point is 0, negative B. Now we're going to talk about the slope of the line that forms this angle theta with the positive x-axis. The slope is rise over 1. And that is the y value, 0 minus negative B, over the difference of x values, A minus 0. And thus equals B over A. Now, hold on. You may have noticed the vertical angles. This is also equal to theta. And now we notice we have a right triangle. And so the tangent of theta is equal to its opposite side, B, over its adjacent side, A. That's the same as the slope. So slope equals tangent of theta. Let's say we have a line that has a negative slope. Let's say that it has lengths B and A on the sides. This point is thus A and 0, and this point up here is 0B. This is a right angle. And the angle that it makes with the x-axis right over here is theta. M going to be equal to 0 minus B over A minus 0. Now it's negative B over A. Now let us think about the tangent within this right triangle. This angle right here, I'll call it beta, is equal to pi minus theta. And so the tangent of pi minus theta is going to be equal to its opposite side, B over A. And so now we can put that in here. The slope of this line is equal to negative tangent of pi minus theta. Now, how do we get the tangent of theta from here? Well, we have to think about what tangent of pi is. It equals 0. So that means that tangent of pi minus theta is just tangent of negative theta. And negative tangent of negative theta is equal to tangent of theta. It's a double negative. And that's that. That is core 8. Whenever you're dealing with a non-right triangle, you use the law of sines, the law of cosines, and the area formula. The area formula is A equals 1/2 AB sine of C. Law of sines says that sine of A over side A equals sine of B over side B. And finally, the law of cosines, C squared equals A squared plus B squared minus 2AB cosine C, or C equals arc cosine of A squared plus B squared minus C squared over 2AB. You would use this if you want to find the area, this if you have 2 sides and their opposite angles, this if you have 3 sides or 2 sides and an included angle. But there's a problem with using law of sines. Certain angles have the same sine values. When you use arc sine or the inverse of sine, your calculator gives you the acute angle. However, there are other angles that would be true, and this is called the ambiguous case. Remember, sine of theta is equal to sine of pi minus theta, and then of course sine of theta is equal to sine of theta plus some multiple of 2 pi. That's the coterminal. When would we have this ambiguous case? Let's say we have a triangle, and we have, let's say that we have angle A, and we have side A, and we have side B. These 2 sides, this angle is not included between these sides. That is a problem. If you think about it physically, this angle is not fixed. This line can move. If it was included, it would be very fixed. There would be only one triangle that would fit that setup. And so there are some specific cases. One case is 2 answers, 2 valid answers. And this is when angle theta and angle pi minus theta are both valid answers. Both of them work within the context of this triangle. Case 2 is 1 valid answer. Both theta and pi minus theta are valid. It just happens that theta equals 90 degrees. It's a right angle. So both of these answers are the same. And then case 3, there's no solutions. And this happens when the triangle that you're trying to find is just literally impossible. You're probably going to get negative sine of some number that's greater than 1, and that's literally impossible. So you're not going to find an answer. That one should stand out to you. What you really have to look out for is when you have a non-included angle given and then 2 sides given. Now, however, case 1 can only happen when the side opposite of this angle is shorter. We should think about it geometrically. We have this angle, and this side, we don't know how long it is. And then here we have A, and that's a set angle. Then we have B is set, and then we have the length of A. And this side is shorter than this side. We can rotate this to be over here, and this is where it intersects. Boom. That's one possible triangle using this length, but it could also intersect over here. Boom. However, if this side is longer than this side, then it could only intersect with this ray over here. Because if you try to rotate it down, it's going to be longer. That's why there are only 2 cases when A is shorter than B. When the opposite side to the angle you've been given is shorter than this side. And that is the ambiguous case. This is core 9. Let's move on to core 10. Oh boy. All right, let's talk about 3D shapes. Core 10. This one's going to be short because I hate it. Let's talk about things in the 3D plane. Let's draw a 3D plane. It has 3 axes. This one right here is Z. The up and down is now Z. This right here, the horizontal, is Y. And this, the diagonal, is X. The way you write out the coordinates is X, Y, Z. To find distance in the 3D plane, it's the exact same. We use the distance formula. The cool thing about this is that since we know how to do it in 3 dimensions, we could theoretically do it in a billion dimensions. We just have to add on a new, like, W2 minus W1 to dictate the position within that dimension. The midpoint formula also behaves this way. You just kind of throw on the Z. Boom. All right, that's core 10. Let's get on to the last core, core 14, quadratics. The final core, core 14, quadratics. If you've made it this far in the video, you're a real trooper. Let's talk about quadratic equations. We have some forms. We have the general form, that is ax squared plus bx plus c equals 0. The things that these letters tell you, these constants a, b, and c, whether or not this is positive or negative, that's going to dictate the concavity of the parabola. So a is also the steepness. A is the distance up that you have to go after going 1 unit to the right or the left from the vertex to reach another point on the parabola. B, that is a part of the axis of symmetry, and so B would impact the axis of symmetry. And C is the y-intercept, which makes sense. If x is 0, only C is left, and C would equal y. We also have a factored form. This is the same A, and these are the roots, the x-intercepts. Their coordinates are R1, 0, and R2, 0. This gives us the x-coordinates and also the concavity and the steepness. Pretty cool. Finally, we have vertex form. Same A, x minus h squared plus k equals y. The point hk is the vertex. That's why it's called vertex form. If you want to convert between these forms, you would factor this one. You would expand either of these, and then you'd use the handy dandy trick using the quadratic formula, in that h is equal to negative b over 2a. That is derived from the quadratic formula, and then you can either plug that in back into this equation to find k. I don't know why you would, because I'm going to tell you right now, I did that for you. K equals c minus b squared over 4a. Let's talk about factoring. You can factor in several ways from this to factored form. What you want to do, I call it the spiderweb method. Some people call it the product sum method. I don't know. You're going to want to find the factors of c and the factors of ax squared. And then these factors, you're going to cross them. You're going to cross them, and then you're going to multiply. And stick with me here. Their products added together should equal b. It's wild. And then once you get those, add straight across to get your factors. So if I call this, I don't know, I'm going to call this J, F, G, I. My factors would be J plus G and F plus I. G times I equals C. J times F equals AX squared. And then G times F plus J times I equals B. We can also factor by completing the square. And completing the square, first of all, you're going to factor out A from AX squared and BX. X squared plus B over A times X plus C. And so now you want to find the number to make this into a new quadratic within this quadratic that would give you a binomial squared. And that number is b over a divided by 2 squared. And since you've added this, you have to subtract it as well to keep the equations balanced. And don't forget to multiply the a again, because you didn't add b over 2a squared, you added a times b over 2a squared. And so the answer is subtract b over 2 squared. This simplifies into x plus b over 2a. It simplifies to this squared, and then plus c minus b over 2 squared. I figured out my mistake. So you know how we had a times x squared plus b over a plus b over 2a squared, and then I subtracted b over 2 squared? That ain't correct. This is b squared over 4a squared, and then this times a, there's still like one a left. There's still an a. So it's actually c minus b squared over 4a. I forgot to mention here that basically by completing the square, you actually get the vertex form, which you can see that because you have the negative b over 2a, and the c minus b squared over 4a. And those were the formulas that I was talking about earlier. Let's talk about the discriminant, aka the thing I constantly call the derivative. It's b squared minus 4ac in the quadratic formula. It's the thing that you're taking the square root of. For the quadratic formula to work, this must be greater than or equal to 0, or else you'd be taking the square root of a negative number, and that would be imaginary. And so, if it is greater than 0, you know that you're going to have two real roots. Two real roots is also called it intersects the x-axis twice. If it equals 0, then the whole second half of the quadratic formula is equal to 0. So there's only one root. Only the vertex is on the x-axis. And finally, if it's less than 0, you are in trouble, because that will give you imaginary roots. It will not touch the x-axis. And from this, when it does not cross the x-axis, it is restricted. It will only be positive y values or only be negative y values. Because if you imagine, if it crosses it, there is a negative y value, but if it's above it, it will never be negative. It'll never have a negative y value. And if it's over here, it'll never have a positive y value. And so if the concavity is positive, if it goes up, and it is floating, it has no real roots, positive definite, and this is negative definite. Alright, so that is using the discriminant, not the derivative. That is a different thing. Alright, now really quickly, I'm going to discuss optimization. Optimization is finding the maximum or minimum of something, basically finding the vertex. If you need to optimize, you're going to want to find the y-coordinate of the vertex. That is what they want, that is what they are asking for, and that is going to be c minus b squared over 4a. Now let's go on to the final thing, which is inequalities. We're going to use sign charts. What is a sign chart? It basically tells you not the sign as in cosine, the sign as in positive or negative of regions of your parabola. So we have our two x-intercepts. We only care about if it's above the x-axis, aka if it is positive or if it is negative below the x-axis. If we have a parabola that looks like this, the area between the two x-intercepts is negative. So we put a little negative sign here. And everything outside is positive. And so, if you have a concave up parabola that has two real roots, and you want to find out what is less than or equal to it, you're going to want all of the x's in this range. And so you would say x can be greater than or equal to r1 and less than or equal to r2. When you flip the concavity, it flips. Now, everything in the middle is positive because it's above, and everything on the sides is negative. And that is inequalities in sign charts. You find the x-intercepts, put them on this handy-dandy line, figure out logistically concave up, concave down, what parts of the graph will be positive and negative in regards to y, figure out what you want. Do you want it above or below? Then you make that inequality. One interesting thing they're probably going to have you do is they're going to say like, oh, what if this is k? And what you're going to want to do, you're going to want to use the discriminant. You're going to want to say b squared minus 4kc, and you're going to want this to be greater than or equal to 0. And now you've made an inequality, and you can now solve for k. You want it to be greater than or equal to 0 because remember, it has to touch the x-axis twice. And so then you just solve that, and that would give you the values of k for this equation. That is the semester review. If you've made it this far in the video, you're an absolute saint. Congratulations. See ya.